our lectures. It's pretty amazing. Thank you for the opportunity. And this slide is to represent the front form, light front quantization, that we see things at the speed of light, like a photograph. And so we see the three quarks of the proton, not at one instant of time, but along the front of a light wave. I'm going to show you a little bit about ADS-5. It's a new way to do physics based on the underlying conformal symmetry of QCD and how you break it. You'll see how that works. So this is using actually a trick from Lucena, from string theory, to actually impact on hadron physics. And I'm going to show you, in fact, the proton. And I always like to emphasize that heavy quarks play a special role inside the proton, that it's unexpected. It's not the way you normally are taught in kindergarten in particle physics. So you'll see, in fact, it's very different. So there's not just a U, D, and C, two U's and a D, but also heavy quarks, of course. So we're going to talk about a lot of these topics here. Color confinement. How do we think about color confinement? And I'm going to show you a new way that we can do this, which is actually sort of remarkable. A way to build in color confinement into the equations of QCD. You'll see how that works. The origin of the hadron mass scale. What determines the proton mass? Craig emphasizes point is a central issue in QCD. You know, if you put the quark masses to 0, where does the proton mass come from? But what's even more mysterious, we don't think about it, is that GeV is not defined in QCD. That's a human convention, electron volts. So in fact, actually, the proton mass is really never determined by QCD, because that's really just our own units. But what is determined is every ratio of every mass quantity to the proton mass. And so that's the goal, is to predict the ratio of every hadron's mass to every other mass and so on, and we'll do that. Okay. Then there's the pi end, a quark-antiquark bound state, but it's massless if the quark mass is 0. And I'm going to show you Craig talked a lot about this. It's really a fundamental point about QCD. And you'll see how this appears in actually a theory I'm going to present, which gives the entire hadron spectrum, the mesons, the baryons, even the tetraquarks, but also gives a massless pi end for 0 quark mass. In some ways, it's astonishing, because how can you have a bound state like the pi end, which has 0 mass? And you'll see how that works. The QCD coupling at all scales. You know, we talk always about asymptotic freedom, about the QCD scale at large momentum, but I'm going to show you, in fact, how to understand the QCD from 0 momentum out to high momentum, and we'll see how this works. Okay. How do you set the renormalization scale? I'm going to do a whole hour on that. This is actually, people often say that we don't know how to fix the scale in QCD. It's too hard, so we'll guess it. But that's nonsense. In QED, we know how to set the scale. That's Gell-Mann and low. And actually, NC goes to 0, reproduces actually abelian theory. So in fact, we actually do know how to fix the renormalization scale, and I'm going to explain how that works. And it cures a lot of problems that people have had in the past. Poincare invariance. Physics is independent of the observer's motion. No Lorentz contraction. You know, one of the myths that you often hear that people talk about in heavy ion collisions, they show hadrons colliding like pancakes. Really? Well, I'm going to attack that. I think that's incredibly dumb. So we'll talk about, in fact, that that's not possible, because it violates everything we know about Lorentz invariance and Poincare invariance. The invariance that physics cannot depend on the observer's Lorentz frame. Rotations or displacements, nothing could depend. A hadron couldn't care less what the observer's doing. So how could one person see a pancake? Okay. Causality, no correlations exceeding the speed of light. This will be throughout my lectures. I'll never want to disturb that. But in fact, people often do. They actually don't realize, in fact, that a lot of things that they talk about are impossible if you respect causality. Light front theory. So we're going to talk about Dirac's front form, light front theory, and the amazing thing is it's Lorentz, it's relativistic, Lorentz invariant bound state dynamics, closely related to the Bethe-Salpeter formalism, but even easier. And you'll see, in fact, how to use the front form in these lectures. Mesons and baryons display supersymmetry. You won't believe this, but there's actually an underlying supersymmetric relationships between, say, mesons and baryons, bosons and fermions. You'll see how that works. We'll talk a little bit about exotic phenomena, color transparency, intrinsic charm, hidden color. exotic hadrons, and a little bit about the cosmological constant problem, but Craig talked well about that already. So light front quantization, I'm going to talk about that because it gives you new perspectives, and once you get used to it, you say, of course. And I always joke that in every planet in the universe where they have civilization, they use front form, light front quantization. They don't even think twice. And you'll see how easy it is and how directly applicable it is to hadron physics. Dirac, who invented it, would love it. So I'm going to show you how we solve quantum field theories using light front Hamiltonian methods. You'll see how that works. I'm going to discuss about light front holography. So that's using information from the fifth dimension. You'll see how that works. And also a thing called superconformal algebra, which you won't believe either until you see it. And then you'll say, my God, that's wonderful, because it actually gives a consistent explanation of so much of hadron physics, dynamics and spectroscopy. It's remarkable. Okay, I've mentioned already the running coupling at all scales, QCD vacuum, novel features. And then also, if I get a chance, there's some things that we believe are true which are not true. For example, the sum rules for PDFs for nuclei, I think, are not true. And you'll see, in fact, why I actually believe that there's breakdown of sum rules. And that's for nuclear structure functions. And then we'll have a whole lecture on the elimination of renormalization and factorization scale ambiguities. So that's sort of the plan. Here, I just thought I'd show this, though, as a preview. This is actually from Klemp and Mesh years ago. They showed, in fact, that if you plot the Reggie trajectories for, say, the delta trajectory baryons, here they are versus J, and then you plot the omega or rho trajectory versus J, they're parallel. Now, if you think about the baryon as 3 quarks, and you think about the mesons as quark anti-quark, there's no way they could have the same dynamics that the mass squared goes up like J. But I'll explain to you, in fact, it's really true. The same Reggie slope is true for mesons and baryons. And it's not only in J, it's also in the principal quantum numbers, the number of nodes in the wave function. They also are identical. There's only one slope that controls everything. That's sort of astonishing. And here's, in fact, a prediction from superconformal algebra where the pion trajectory versus L, that's the internal orbital momentum, is exactly, m squared versus L is exactly parallel to the nucleon trajectory. So this is also astonishing. But there's also, if you notice, the pion sits alone. The first excited of the pions is degenerate with the n. This guy's degenerate, approximately. And you'll see these formulas for the mass squared of how hadrons depend on the internal angular momentum and the principal quantum number. So this is pretty interesting. And so you get ratios of mesons to baryon mass, nucleon masses, and all sorts of fun things. And here's another example of this, where you take the rho trajectory and the delta trajectory, and you plot it versus internal orbital momentum, and you find, in fact, that they sit on top of each other remarkably. And in some sense, then, the rho trajectory and the delta trajectory are not only are parallel, but their masses are the same if you make the substitution of internal orbital momentum of 1 unit. And then what happens is you actually have superpartners, that the mesons and baryons are actually superpartners. So you'll see how to derive this, and that'll come later. So again, we're taking mesons and baryons and showing, in fact, that they really have the same spectrum. But this is experimental data. It's remarkable. And I'll show you how to derive this formula later. Okay. So bosons and fermions have the same mass. It's a type of supersymmetry. And what I'm going to derive for you is a new type of Schrödinger equation. So right now you don't know what these mean and so on, but this is like d by dx squared, LL plus 1 over x over, let's say d by dr squared, LL plus 1 over r squared plus a Coulomb potential. There's something like that, but in light front QCD, which actually, if you solve it, it gives, in fact, the hadron spectrum and all their light front wave functions, so then you can compute phenomenology galore. And I'll show you how this is derived. It comes from anti-de Sitter space, the so-called softball model, a light front holography, which is the connection between anti-de Sitter space and our world in front form. You'll see how that works, and you'll see how these equations come in. And this variable zeta squared plays a key role in hadron physics. It's the radial variable, not of the Schrödinger theory, but of this light front Schrödinger equation. It's actually x1 minus xb perp squared, and you'll explain where this comes from. It's like the radial variable of low energy non-relativistic Schrödinger theory, and so on. And this theory, though, when you put in the potential, which is kappa 4 zeta squared, a harmonic oscillator in this radial variable, and these spin terms, it reproduces the hadronic world in a remarkable way. And it's based upon not only ADS5, but a new principle called conformal symmetry of the action, which is really pretty remarkable. It goes back to an old paper by D'Alfa, Frubini, and Furlan, which says, amazingly, that you can introduce a mass scale into a theory which doesn't have a mass scale. It gives you masses in the equation of motion, like this scale kappa has got mass dimensions. However, you still conserve the conformal invariance of the action. And this paper is a really remarkable paper. They didn't believe it themselves because they proved this thing 3 times in their papers, so they couldn't believe it. So you'll see, in fact, if you use that principle, it tells you this is the only possible confinement potential. So you'll see how this works. All right. I'm also going to show you what supersymmetry does for you. It actually organizes the hadrons into 4-plets. Mesons, which are quark-antiquark, the black is antiquark. Diquark-quark baryons. We just heard Craig talk about quark-diquark proton. And then the tetraquarks, which are diquark, anti-diquark. And they all, in fact, are fundamental hadrons. They all come from the superconformal algebra, and they all have the same mass. So it turns out that the 4-plet organizes mesons, baryons, and tetraquarks in an amazing way. And you'll see how this works. All right. And these are going to be the equations for both mesons and baryons that we'll derive. And these are very simple. So this is basically an introduction to where we are. It shows, in fact, that the mass spectrum of mesons and baryons are almost the same, except the 1 unit of L difference. You'll see how that works. So in fact, you get the same mass spectrum if you shift the L of the mesons by 1 unit. Here's a little bit more of this. The pion trajectory is parallel to the proton trajectory, and the rho trajectory is parallel to the delta trajectory. Comes out of that simple equation. And here's more. In fact, it shows the Reggie trajectories and how they fit the formula I just gave, both in L and N. And also, we heard a lot about form factors. Recently, Nikita Sharma just took our formulas and just compared with the literature on the proton and neutron form factors, isolating the up and down quark contributions. And you just take the formulas that you get out of those simple equations, and you get beautiful representations of the nucleon form factors. So we'll talk about that. So I'm going to tell you then about light front wave functions, which are extremely important. Craig emphasized that. They're the things we actually underlie all observables, form factors, structure functions, and so on. We actually have pictures of them. Now you'll see this the mesons for the pi and the rho and so on. This is the fall off in K perp and the behavior in X. And you'll see how this works, and you'll see how one way to derive it is from anti-de Sitter space, and you'll see how that comes out. Okay. So again, this is all introductions. I'm going to go back through all these things later. Everything, again, measurement like a photograph at fixed light front time. I just had to give you a little history because I was at SLAC when the 2-mile accelerator turned on. And here's the PIF who designed everything, the 2-mile accelerator. At the end of it is, in fact, the end stations where they actually have spectrometers like this, and they measure deep elastic electron scattering. Here's, of course, the canonical picture. You're measuring, the electron is measuring breaking up the proton. The signal goes at the speed of light through a photon. So it's really like a photograph. So here's the first graph. It showed the structure function we now call F2 is actually basically flat in Q squared. But it turns out they were lucky to get such a flat distribution because they actually picked X of 1/4. Here they actually use the variable omega, which BJ introduced, and 1 over omega is XP arcane, and they worked at X of 0.25. And they were amazed to find out there is no Q squared dependence of this result. And so this was, in fact, the beginning of what's called Bjarkian scaling. And it actually, the fact that you don't have any Q squared dependence means there's no intrinsic length scale. it's really telling you, in fact, you're dealing with point-like constituents inside the proton. So this is really a remarkable discovery. And this, of course, back just when I came to SLAC in the early 60s, was this was the secret of the universe right here. And the fact that, in fact, this cross-section is independent of q squared, it's really q to the fourth times g sigma to q squared, which is what we plotted, is just a function of x p arcane, independent of q squared. That's remarkable. Of course, now we know this is a little bit of illusion that there's logarithmic variation from deGlap evolution and so on, but still it's there. So this is really the first evidence for the quark structure of matter. This is the Parton model, and that includes, in fact, the gluon radiation from the initial and final states, which gives us deGlap evolution. So this is still, in fact, our underlying story about how we think about the proton structure function. But the question is, though, first of all, why do hadrons only appear in the final state? So here you produce a jet, a quark jet, gluon radiation. Why are quarks always confined in hadrons? So how is that possible? That's really the dilemma. Is that, you think about E plus E minus goes to photon, goes to quark antiquark pair. The quarks make gluons. The gluons make more quark pairs. You can end up with 50 quark pairs, 100 gluons. They all end up in hadrons, right? That's quite a problem. Okay. So when the Bjorkian scaling happened, it turned out that Feynman was actually visiting SLAC. His sister lived in Palo Alto. And when he saw the data, Manny Pascas, who was a postdoc at the time, showed Feynman data. And he says, my God, that's my Pal. And in fact, he actually applied the Parton model to deep elastic electron scattering. In fact, he did it overnight because he said in the morning that he never thought about applying the Parton model to lepton-proton scattering. He only thought about it for proton-proton scattering, about how, and he basically had the picture that we always have. And then he applied it to deep elastic scattering, understood what X meant, and so on. So that's pretty amazing. So here's Feynman. Here I show a picture of George Zweig. He invented aces, deuces, and trays. People forget this. Just at the same time that Gell-Mann invented quarks. And here's the Gell-Mann's picture. Actually, Gell-Mann came to SLAC a month after Feynman, and he says, why does Feynman call it the put-on model? He knows they're quarks. I heard him say that. Well, actually, Feynman understood, in fact, that there had to be gluons, too. You couldn't just have quarks. So he didn't want to totally commit himself to quarks. At that time, Gell-Mann was totally committed, even though a year before, he thought they were mathematical objects, right? And then Bjorkian, of course, invented the scaling. So we really, in fact, have this wonderful picture then of the proton, and it's got three quarks with three colors. Well, where does that come from? I think you all know the story. This is Wally Greenberg's contribution. He thought about the delta plus plus, which is three up quarks. If they're all in J z equals plus 3 halves, the three quarks, of course, have parallel spin. It violates Pauli statistics. So he said there must be three colors, a new quantum number called the parastatistics that solves the paradox. And of course, that was the beginning of SUNC. There had to be three colors just to get around this problem. And that's Greenberg. And in fact, I just wanted to show this old historical thing, that in fact, if you do the cross-section for hadrons over mu pairs, then in fact, you see, in fact, exactly the right gap as you keep going up in charge squared, as you keep making more and more quark flavors. You also get a factor of 3 for the number of colors, and this was the first real strong evidence that color is really right, a dynamical thing. So it's perfect. Now, Gell-Mann and Fritsch and Leutwiler invented the Q-city Lagrangian and so on, so we'll come back to that. All right. But delta R goes up just right between the charm quarks and the bottom quarks. Okay. And then, of course, you also see the resonances like the J psi, the psi prime, and the upsilon. So all this, in fact, was done also pretty much at SPEAR, too, which is the first real electron-positron collider, in fact. It's not really the first ones, but the one that really did everything and saw the J, for example, the psi. So evidence for quarks, the scale invariance of electron-proton scattering. We have the annihilation cross-section, just with the three colors. You also see that if you look at the hadron multiplicity, along the quark jet versus the gluon jet, you see the color factor that you expect, 9/4. In fact, it shows that gluons really have more colored charge than the quarks. Exclusive hard scattering reactions is something I contribute a lot to, which is actually the scaling laws for every reaction at hard momentum. PP scattering goes like 1/s to the 10th, exactly predicted by conformal invariance of QCD. Gamma p to pi plus n goes like 1/s to the 7th, just by counting constituents, and form factors obey counting rules. And so then, in fact, you can use, in fact, the underlying conformal invariance of QCD to predict, in fact, the counting laws. That was, we already heard from Craig's lecture. The form factors fall off generally as 1/q², the number of constituents minus 1. And the differential cross sections, say for PP to PP, there's 12 constituents, so you predict 1/s to the 10th, and the data is 9.7 plus or minus 0.5. So it's all works, and here's people who contribute to that. And also, there's another thing that people probably don't know, which maybe I'll show a slide on, which is quark interchange. And if you take two hadrons, they actually typically interact at large momentum transfer by exchanging their common quarks. And that actually explains the angular distribution, not just the scaling law, but actually the angular distribution. For example, if you do K plus P scattering, the kaon's got a up quark and an S bar. The up quark can exchange with the up quark and the proton, and that gives an amplitude, which is 1/u, 1/t². You square that, you get, in fact, the right angular distribution and the counting laws. So here's a famous plot, the beta function, the first derivative of the running coupling. And the beta function, of course, is given by 11/3 NC, and C is 3 minus 2/3 NF from the quark loops. And that's the logarithmic derivative, shows, in fact, the coupling does become negative, so the running coupling becomes negative, and of course, this is the standard that you all know of asymptotic freedom. And it gave the Nobel Prize to these guys, Gross, Wilczek, and Pautzer. And you can see this also for the ratio of 3 jets to 2 jets. You can see, in fact, the running coupling, just what you expect from asymptotic freedom. And now, I thought I'd show this plot, though. If you go to a theory like SU5 to unify QED, QCD, and electroweak theory, QED, normally this 1/alpha has a Landau pole. The QCD goes up. Now, people often show this plot, and I always get bothered by this, that they show at the grand unified point that the 3 couplings become equal at the grand unified scale. But that's not true. If you actually do the analysis, you find out they never cross. They just simply become asymptotically equal. So the textbooks are often wrong on this. I mean, it's sort of astonishing. Because if you put the heavy masses into the grand unified theory, you have to put that in analytically. And you can't have 3 lines cross at a point and then go off in a straight line, because that violates analyticity. The derivative's not continuous. How can you do that? Some people understand that, and they draw the 3 they draw them coming at a point, and then the 3 going off in different directions. That's even more silly. If you do it right, Binger and I showed this, you get asymptotic unification. You can say within 1% they're the same at the grand unified scale, but they never cross, and that's a big mistake. Yes, so then, of course, you're right. So then, good question. When you unify, of course, they all go into eliminate the Landau pole. Yeah, so this is the incentive, in fact, for things like supersymmetric SU5 and SO10, just to make this happen. Absolutely right. So that's perfect. And so here, this is a complete calculation with the masses of the heavy particles in. You actually get this curve. But another reason why I wanted to show this is that people know how to set the renormalization scale in QED. If you do electron-muon scattering, 1 photon exchange is alpha of t. It's trivial. Just sums up all vacuum polarization graphs to all orders. Okay, but then they say we don't know how to do this scale setting in QCD. How can you do grand unification if you know how to do the scale setting in QED and you don't know how to do it in QCD? Are you crazy? Of course you know how to do it, and they have to be exactly the same method. And that's called BLM, Brodsky, Lepage, and McKenzie, or nowadays the principle of maximum conformality. And you'll see how that works. All right. So if you actually put NC to 0, just for fun, then you see, in fact, that you get the QED beta function. This is just the terms from vacuum polarization. So in fact, people often think that you get a billion theory by putting NC to 1. No way. Get the wrong answer. If you put NC to 0, then in fact you get the QCD goes to the QED. In fact, that's the right answer. In fact, in QED, you get this only term. It's the beta function's positive. It's got the Landau singularity, and so on. And that's, of course, the problem with the short distance behavior. But the main lesson of this is it's NC equals 0, right? Then, in fact, there's a rigorous limit. And this is something that Patrick QA and I wrote, I'll talk a little bit about later, which is that the actual analytic limit in NC, think of NC as an analytic variable Z. If you put Z to 0, you go from none a billion to a billion theory. And so anything you do in QCD has to be correct for QED and the analytic limit NC goes to 0. Okay. And here's the statement. If you actually take NC to 0, fixing this product, CF alpha strong, CF is actually singular as NC goes to 0, but the product is a finite number alpha. Then, in fact, you find, and this also there's a trick on the number of leptons, you find that QCD becomes a billion theory. So this is actually an analytic feature of SUNC. Now, the first thing that when you look at this, you say, I don't believe it, because if you take SU of NC and you put NC to 0, you get nonsense. However, if you think about it as U of NC divided by U of 1, that's the definition of SU of NC, and then you take the limit NC goes to 0, the numerator becomes 1, the denominator is 1 over U of 1. In fact, the group you get is actually a billion theory, not exactly the same as QED. It turns out that light-by-light scattering is off by a factor of 2. It's really interesting. In fact, QA and I, we wrote a paper where we showed how you compute the defect between ordinary QED and this 1 over U of 1 theory by just counting the number of vertices and legs in a graph. And then you actually can get the theory. But it's so close to QED, the distinction is minor. But it's really interesting to see this analytic study, in fact. It's 1 over U of 1. That's pretty interesting. But again, the lesson is that you better use the same scale setting method because you can never get, if you say that you're going to guess the answer in QCD, which is what you hear in every talk at the LHC, right? Every talk at the LHC, they start out, we don't know how to fix the scale, so we'll guess it. You hear this all the time. Then how could you possibly unify with QED? Because you'll get the wrong answer if you guess in QED. Nobody would ever, in a million years, guess the answer. Every precision calculation, you set the scale by absorbing vacuum polarization graphs. It's trivial. All right. So we're going to talk about Dirac's front form. One of my favorite subjects, and here's a picture of Dirac. And what's the point? The measurements are always made at fixed light front time, T plus Z over C. This makes sure that causality is automatic. Then you find out that you'll see this, the structure functions are squares of the light front wave functions. The form factors are overlaps of light front wave functions. The light front wave functions are frame independent. They just, as you expect from hadron physics, everything has to be Lorentz and Poincare invariant. There's no pancakes. And the first people who really showed this was Terrell and Penrose. They showed, in fact, that you never would see such a thing. That's a pancake. And when you think about the formula for Drell-Yan's to mu pairs, right? P bar goes to mu plus U minus. The answer doesn't depend on the frame of the observer, just the product of structure functions. There's no pancakes. So how could you possibly ever believe there's pancakes? And if you're in a spaceship and you're moving close to the speed of light, by somebody else's reference frame, I guess, then are you squashed to death? Of course not. There's no change. So how can people possibly believe that the initial conditions in a heavy ion collision is pancakes? It just boggles the mind. And I've been told that every time a experimentalist gives a talk at Brookhaven on heavy ion collisions, they first see if I'm in the audience. And then they eliminate the pancakes. But it's obviously nonsense. Physics cannot depend on the Lorentz frame of the observer. That's number one principle. Okay. So that's this point. The same structure function will be measured at an EP collider as the proton the rest frame. There's not a different answer, right? When they build the electron collider, ion collider, they're not going to say, we're not going to see the same answer because the proton's moving. Come on. You know. Light front holography, we're going to discuss that. That's this amazing duality of ordinary physics in the light front to ADS space. The light front vacuum is actually simple because in the front form, there's no graphs where you just get two particles coming out with opposite plus momentum. It can't happen because the plus momentum is conserved and the vacuum has zero plus momentum. And that has profound implications for the Cosmological constant. And that was discussed a lot by Craig yesterday. Okay. So here it is. Here's this picture that you see, in fact, all the time in the heavy ion collisions, that you boost and somehow you have a pancake. Actually, I gave a talk in Mexico about this, and I called it tortillas, you know, the colliding tortillas. Really? Of course not. You will never, the nucleus is not squashed, and it's a total mistake. And the mistake is that people think about Lorentz contraction. They learn about it in high school, you know, and then they say it must be true for this. But actually, that's not really true, because you only make observations at the speed of light. What that Lorentz contraction refers to is if you could actually see the whole object at one instant of time, which violates causality. So that's the mistake. And of course, the whole thing violates Lorentz invariance. Weisskopf also wrote about this besides Penrose. We do not observe the nucleus at one time. We observe it like in a movie or in a photograph at one light front time. So here's Dirac's contribution in 1949. He compared the instant form, which is with ordinary time, with the front form, where in fact you use the variable t plus z over c. And he realized right away the significance of this, because boosts from one Lorentz frame to another frame are just trivial kinematics in the front form. If you do an instant form boost, you have a dynamical problem. It's as hard to boost a wave function in the instant form as is to solve the problem in the first place, the bound state problem. You can't do it. It's incredibly difficult. In the front form, it's trivial. So what are we doing? We're using the variable t plus z over c, and that's actually the variable which is tangent, the time tangent of the light cone. So it's in Dirac's honor, he called it the front form, and nowadays I think the right terminology is light front physics, not light cone physics, because it's nothing involves the cone at x squared equals 0. It just involves this new light front time, and that's what he talked about. So here's an illustration. You take a photograph. You're seeing, in fact, the light strikes the horse's nose before the tail. You're not looking at the horse at one instant time, the statue. You're looking at the time that goes, the light front time, the time that goes across the object. So the right thing to do is introduce tau, which is t plus z over c. And the conjugate variable is p minus. So I'm going to introduce p plus and p minus, p0 plus pz. So this is like t plus z. Everything is going to be causal, frame independent. You'll see that. You evolve in light front time as you change the light front time, like making a movie. That's the light front Hamiltonian. The time evolution operator is p minus I d by d tau. The eigenstate is the state that's independent of tau. The eigenvalue has the form p minus is mass squared plus p perp squared over p plus. In the front form, the p plus doesn't change. Only thing that changes is p minus. And p minus is related to the m squared, because if you multiply p plus times p minus and subtract p perp squared, you get m squared. So actually, you're really involving an invariant mass. So what we do is we define what's called the light front Hamiltonian. You take p minus multiplied by p plus, which is just a number, minus p perp squared, and you get the light front Hamiltonian. And the eigenvalues of this Heisenberg problem is m squared. So every hadron in QED, every atom in QED is actually a bound state problem, which is the eigenvalue is this. And these are the eigensolutions. So it's as simple as ordinary quantum mechanics, but you're just changing the time variable. All right. So Dirac says, working with a front, he meant light front, is a process unfamiliar to physicists, hopefully not after these lectures. It'll be very familiar. And he says that mathematical simplification is all important, and that's absolutely right. And over the years, he understood, in fact, more and more that the instant form is useless. And he said that in 1977. So here's a picture from Silas Bean, which shows, in fact, the light front direction, tangent light front, and then another rotation variable, which we'll use, which is actually how you go around in a circle and how you project out states, the given Jz. We'll see how that works. All right. So in deep elastic electron scattering, we're going to construct the light front wave functions. These are functions of x, k-perp, and spin. So let me explain what that means. So we start out with a state with arbitrary p plus, arbitrary p perp. Those numbers depend on the observer. The hadron will have momentum xi p plus. This one has x1 p plus, x2 p plus, x3 p plus. It also picks up p perp, xi p perp, and then it has an extra k perp. So what these are is actually the true dynamical variables, the x's and the k perps and the lambdas. And these quantities will not depend on p plus or p perp. So that's the magic of Dirac, is that boosts are trivial, because boosts just change p plus and p perp, but this quantity never changes. So again, we're looking at fixed light front time. And here's a little bit more about details. Here's, again, the wave functions. What are they really? What you're doing is actually taking the eigensolutions and constructing a Fock basis. So this came up in the last lecture too, is what you do is you start with a vacuum, which is empty. You create particles with momentum k plus and spin projection lambda. This is the direction of spin in the z direction. And n, the number of quanta. So first what you do is you construct a Fock basis, a free Fock basis, the eigensolutions of the free Hamiltonian. Then you solve the true problem, the eigensolutions of the true light front Hamiltonian. You project it, for the case of the proton, on three quarks and a gluon, it goes on forever. And each of these wave functions then is the things that are the observables. They're the frame-independent Poincare invariant quantities. The sum of the x's is 1. That's because in the front form, momentum conservation means that plus momentum is conserved. So the sum of all these particles here have to add up to 1. So the p pluses, there's an x1, x2, x3. The sum of the x's adds up to p plus. The sum of the xi's, x1, p plus, and so on, they add up to p perp. And then the k perp is free, but the sum of the k perps is 0, because that's just the internal momentum. So this is how the wave functions work. Each of these wave functions, this is the three-quark valence wave function, xi, k perp, and lambda. And it's invariant under boost, independent of the total momentum. The only thing it depends on is p mu squared, which is the mass, of course. All right. This formalism is causal. Nothing goes faster than the speed of light. Frame independent. Nothing depends on the observer's motion. The creation operator is in a simple vacuum. That's the front form. And current matrix elements are simple overlaps of light front wave functions, and I'll show you how that works in a little bit. All right. So here again is the key equation. H light front QCD, for example. This gives you, in principle, the entire spectrum of hadrons, just by solving this problem. So you first have to construct the Hamiltonian. That's a standard method. You go from the QCD Lagrangian to the Hamiltonian, and you get this answer. So here's a little review of the notations. Tau is sometimes used for x plus, x minus is the conjugate longitudinal variable. X perp is just like old-fashioned physics, transverse variable. And then the conjugate momentum are here. The on-shell requirement is this dispersion relation that p minus is p perp squared plus m squared over p plus. Here's the eigenvalue equation. The eigenvalue for p minus is this guy, but when you multiply p minus by p plus, subtract p perp squared, the eigenvalue is m squared. So in fact, this is the simple way to understand physics. So the wave functions then have these properties that if any p plus doesn't matter, what it is, you get the same answer. Psi doesn't care at all what P plus or P perp is. The K pluses are K0 plus Kz. The ratio K plus over P plus is what we call the light front fractions. Those are the quantities that actually are measurable. This formalism does reduce down to Schrödinger non-relativistic physics. If you just take the limit, non-relativistic limit, you get the ordinary Schrödinger theory. But this is the relativistic version of it. Momentum conservation, the sum of the K pluses, I should have I equals 1 to P plus. The sum of the xi's is 1. The sum of the K perps is 0. Angular momentum conservation. This is really important. So normally in particle physics, people use helicity. And that's spin in the direction of motion. It's not conserved because you're just letting every particle going off in its own direction. In front form, you pick one direction, the same direction you pick in the original thing to define the plus momentum. So just pick that. Then what happens is that Jz is conserved. Every interaction conserves Jz. Every wave function, every Fock state, they all conserve Jz. And Jz is broken up into the internal spin and the internal orbital momentum. I'm sorry. When you say Jz, yeah. No, it's the same spin that you're used to, but in the z direction. And in fact, there's 2j plus 1 degenerate states from minus Jz to plus Jz. So it's exactly the same as Schrödinger theory that you're used to, but it's not helicity. So if you start out with a state of given Jz, you end up with a state of given Jz. You can't violate that. So this eliminates millions of things that people don't realize. It's calculating amplitudes which are 0. You don't have to do that. So the front form has this simplicity. You should just use Jz. Every particle, you project its spin in the z direction. The particles can be moving in every direction in K perp, for example. However, you still can measure its spin along a given direction, which we call z. So the first thing you do is you make a convention of what the z direction is. And that's the light front thing. And then that same z is used for this. All right. Now, what turns out also is interesting is that it turns out that normally when you think of wave functions in K perp and X space, you think they're two separate functions. That you get, people often do this in phenomenology. They write that the wave function is a function of K perp squared, maybe a Gaussian or a power law, and then another function of X. Not true. Turns out they always come in like this. K perp squared is always connected to the X distribution. And that's rotational invariance in the front form. That's the consequence of this. So in fact, it turns out then that the K perp squared is not a separate, cannot just go off separately. It has to be tagged with X. And that's another new insight and so on. But these wave functions, they underlie all observables, and we'll go through a lot of them. Okay. So this, what we're looking for now is using the front form to get an equation, a first approximation of QCD that's as simple as Schrödinger theory in atomic physics. Here's Schrödinger. But it has to be relativistic, frame independent, color confining. We have to understand how the mass scale comes in. I'm going to show you this approach to it, which is rather remarkable. We want the QCD couplings at all scales. We want to explain hadron spectroscopy. We want to explain their wave functions. We want to calculate all the phenomenology, form factors, structure functions, and so on. You can derive counting rules immediately from this. Hadronization of the amplitude level. Well, I told you before, there's a problem of how the hadrons, quarks and gluons turn into hadrons. No problem. These wave functions take you from the off-shell quarks and gluons to the hadrons, so we'll talk about that. Chiral symmetry and systematically improvable. Well, I'll explain that this approach is just the first approach to the hadron physics. It's not the exact light front Hamiltonian, it's the first approximation, but it's improvable, and I'll show you how that works too. All right. But then this key problem, what sets the QCD mass scale? How does the proton get to be its mass? Okay, so then to review, measurements are made at fixed light front time. You can't, that guarantees causality. We'll see structure functions are just the squares of these light front wave functions. For example, the structure function measured deep elastic scattering is the square of the light front wave function, integrate over all the K perps, and the only thing that's missing is that the one quark that struck, its x is the x Bjarkane. Form factors, overlaps of light front wave functions. So Craig mentioned this. There's no formula in instant time. I'll review this. Nobody has ever computed correctly a form factor in instant time. Front form, it's simple. Okay. And then there's the vacuum is trivial. There's no condensates possible, and that has profound implications for the cosmological constant. All right. And underlying this is this point that ADS5 in the fifth dimension is actually dual to our world. You'll see how that works. All right. So here's the famous QCD Lagrangian, Gelman, Leibweiler, and Fritsch. And it's based on the Yang-Mills gauge principle that you can rotate color as long as the phase at every point in space and time. And of course, it's gauge invariant. It has a scale invariant coupling. It's renormalizable. It's almost conformal. It's not exactly conformal, but we're going to use this almost conformal in an interesting way. Asymptotic freedom is built in, and color confinement. Nobody's really derived color confinement from this Lagrangian, but we all believe it happens, right? Yeah. And here's the couplings. You know, the quarks couple to a gluon, which has got 8 possibilities, 3 cross 3 minus 1. And then there's the 3 gluon and the 4 gluon coupling, all comes from the Lagrangian. And here's the basic thing that you all know. And in QED, you get the same vertex, but no analog of the 3 gluon and 4 gluon coupling. And that all comes from this Lagrangian. These things, the G squared term, you put in G, which is d nu minus G A commutator A. And the squared term is the 4 gluon coupling, and the interference term is the 3 gluon coupling, because it's just from the square here. If you go back to QED, it's the same thing with F mu nu, F mu nu. Okay. So now we think this is the fundamental theory of not just hadrons, but also nuclear physics. And we have this principle. And now the point is, let's put the quark mass to 0. What happens, right? That's, you know, the quark masses evidently come from the Higgs theory, so let's try it, right? The theory shouldn't care. But now we really have this problem. Where does the mass scale come from? Classically conformal, there's no mass scale. But in fact, quantum theory, it's not exactly conformal, and Craig emphasized that. And the QCD mass scale that comes from confinement is not explicit. But as I mentioned, though, we should hold on for a minute. The mass scale in electron volts is never determined. The theory can only determine ratios. It can never determine the absolute mass scale. So here's the Lagrangian of QCD. This is the light front QCD Hamiltonian. So what you do is, to derive the Hamiltonian, that's standard rules in quantum field theory, you eliminate the redundant degrees of freedom. In the case of what's particularly advantageous in the front form is use what's called light cone gauge. That's A plus equals 0. Somewhere it's written up here, I don't know. But if you do A plus equals 0, then a miracle happens. So that's sort of like Coulomb gauge, but it's frame independent. It's a wonderful gauge because there's no ghosts. There's there's no problem at all with the theory. But however, what then happens is that the fermion fields, there's an upper component, like in Dirac notation, to upper component and lower component. The lower component can be written exactly in terms of the lower component if you put A plus equals 0. So then, in fact, you can do all the dynamics in terms of the upper component, eliminating the dependent degree of freedom. And that's what's done here. In fact, it turns out then that when you do that, you get, in fact, this extra term right here. This term comes in. It's a local Siegel term, and it comes in because I've eliminated the lower component. I'm going to stop in a minute, okay? A lower component of the fermion field. And then introduces a Siegel-like term, 4-point interaction. In addition, this term, in light cone gauge, it has a Coulomb-like interaction. It's instantaneous in light cone gauge. It has a form of 1 over k plus squared. And so the penalty for eliminating the ghost and degree of freedom is actually introducing, in fact, an extra interaction. But that's exactly rigorous. There's no approximations here. So in fact, you can just calculate that using these rules immediately, the front form Hamiltonian. So given the light front QCD Hamiltonian from this procedure, it turns out that the Hamiltonian has this form. The free part, which is called the light front kinetic energy, that's m squared plus k per squared over x. If you sum this over all the particles in a given state, it's the invariant mass squared of all those particles and the interactions, which are here again. And so this equation becomes a light front equation. And again, what I said before, the eigensolution is then the wave function for each Fock state on the free Fock basis. And that's the state. Okay. So the eigenvalues and the eigensolutions of this equation is the hadronic spectrum and the light front wave functions. And I'll explain more about this when we come back. All right? Very good. Okay. All right. This. Okay. Just wait one more second. Okay, very good. All right. So this slide is an important slide because it summarizes the whole underlying formalism of solving quantum field theory in the front form. And this equation, we'll see how to solve it in a moment. And these are the eigensolutions for the protons, starting with the 3 quarks. And these are the interactions that go into the Hamiltonian. So there's a free part, which looks like p squared over 2m, but it's actually the invariant mass of the entire system. So if you sum over I and compute p4 vectors squared of all the particles, that becomes this for the free particle. And here's the interaction. So in fact, when you look at this eigenvalue, the first part is the free part, and all the rest is the interaction. So it's very similar to non-relativistic physics. And then to emphasize, the eigenvalues and eigensolutions are the hadronic spectrum and the light front wave functions. And I'll give you examples of how we've solved that, in fact. Okay. The light front wave functions are off shell in P minus, if you like, but on shell in P minus. That means in invariant mass, the eigensolution is fixed in m squared, but the particles that appear in the Fock state are off shell. Just like in Schrödinger theory, the wave function is on shell, but the constituents are off the energy shell. Here they're off the invariant mass shell. Okay. Now, as an example of light front perturbation theory, the T matrix is the interaction, energy denominator interaction. But in the front form, it's the invariant mass squared to the initial state minus the invariant mass squared to the intermediate state. So there's nothing with energy. Energy never appears because energy is frame specific. M squared is not. So then you can compute matrix elements of T, I, J, and so on. It's standard. And all particles are on their respective mass scale. That is, every particle has 4 vector squared m squared, but of course the state is off shell in m squared. That is, the sum of the m squareds of the constituents does not add up to the overall m squared. So the whole thing mimics old-fashioned perturbation theory, except you're exchanging energy from invariant mass squared. And then also, you have these conservation laws that the plus momentum in p perp is conserved at every vertex. Do you want to fix this? Thank you. Yeah, I don't know what I'm doing with it. Yeah, every interaction conserves plus momentum and perp momentum in JZ. The sum of the k pluses is that. This is just the condition. The sum of the x's is 1, for example. And then also, oh, now you're turning up too loud. All right. Also, there's another rule which Kelly Chu and I developed last year, which is interesting, and that is that in a renormalizable theory, the orbital momentum can only change by 1 unit or less, or 0. So if you look at a vertex in a renormalizable theory like QCD, the vertex can only flip the orbital momentum from the initial state to the final state by 1 unit. That's the maximum. So then when you look at amplitudes, like the Park-Taylor amplitudes, 2 gluons go to 15 gluons and so on, you can see right away which amplitudes are 0 and non-zero at any order of perturbation theory because the L can only change by 1 unit at every vertex. Okay. So here's another example here where this is just scalar theory. A plus B goes to C goes to D plus E. And you put in the initial state m squared, which is just S. If you compute S, it's Ka plus Kb squared, and that's given by this formula. And then you compute the intermediate states. And immediately you get the standard answer that this is just given by S minus the pole of this guy, mc squared. So it just, immediately you get the same answers as Feynman rules. And it becomes S minus mc squared plus I epsilon. So it's just an exercise just to see how familiar you are with, in fact, just doing perturbation theory. Okay. So some distinctions that you don't think about. All intermediate states propagate, each particle is on the mass shell. This is not Feynman rules. Feynman rules, you have 4 vectors squared, not m squared. That's different here. Here, each particle stays on its mass shell, propagates on its mass shell. This is old-fashioned perturbation theory in the light front. However, the invariant mass squared is not conserved. The Wick theorem. So the Wick theorem, if you start with Feynman rules, what's going on with this thing now? Yeah. No. Maybe you think it's my phone, huh? All right. Okay, stop now anyway. All right. No. Terrible. You're right, here's my phone. All right. Okay. You learn new things every day. All right. So the Wick theorem tells you that you have to sum over n factorial time order diagrams. That's instant form, old-fashioned perturbation theory. It's a horrendous calculation, and that's the reason why nobody did instant form after 1948. They just gave it up, because every graph is frame dependent. If you add all n factorial diagrams, you get the Feynman answer, but it's hopeless. In front form, you have very few diagrams. Only the ones with positive plus momentum come in. Because plus momentum is K0 plus Kz, and K0 is greater than Kz. So you only have the graphs where every line is, if you like, forward moving in the plus direction. Then you have integrals. Instead of d4k, the integrals are just integrals over 3 dimensions, d2k perp and the x. So when you start doing calculations, you find out they're only 3 dimensionals. Each amplitude is frame independent. Each amplitude doesn't care about the observer's motion. That's very different than old-fashioned perturbation theory. Unitary is explicit. When you do a calculation in light front perturbation theory, you can just take the imaginary part and see the unitary rule immediately. You don't have to search for it like in Feynman. History. This is a very strange thing. It turns out that because all the particles are on the mass shell, when you do your spinor algebra and sum over polarizations, it doesn't matter what the context is. The numerator algebra is identical. So what that means, in fact, when you compute things in light front theory, you don't ever have to compute the same amplitude ever again. The only thing that changes is the denominator, and that's the context dependence. So if you're smart, you can start with a 4-loop calculation and do the 5-loop with starting the same place because the numerator algebra is the same. And when you have cluster decomposition, every cluster has the same rule. You don't have to do it ever again. Now, I call it history because in LaTeX it, if you type a formula in LaTeX it for your PowerPoint or your Keynote, you never have to compute it again. You have to print it again. And that's the same thing here. You can store every amplitude once and for all and never do it again. So this is very much different than Feynman. Feynman, you have to start all over every time. You don't here. All right. JZ conservation of every vertex. And here are the spin projections along Z. So here's another calculation, 2 particles scattering. They exchange a particle right here. And you just put in the initial state minus the intermediate state, and you get T minus lambda squared plus I epsilon. Just from this one diagram, you get it right by choosing, in fact, the frame where this guy can only go positive sign. So then you get a formula for T, which is Q squared minus Z squared M squared 1 minus Z. So just by, we don't have time to go through every analysis here, but just by choosing Q perp and Z, you can get T. But you have freedom, though. You can put Z equals 0 for these amplitudes and so on by choosing the frame where this guy has the same X. And then this guy has got Z equals 0, and then there's no plus momentum that moves this way. And this is a trick that Drell and Yan and West invented, which is, in fact, you can write T in the very simple form as just minus Q perp squared in this graph. So that's a trick, and we'll use that trick. All right. You can also do self-energy graphs. So you put in graphs like this, and you just have initial invariant mass squared minus intermediate, and so on. And then you get this graph immediately gives you the Feynman rule for sigma of t. I always joke, in a different planet, this is the way they never discovered Feynman rules. They never needed them. It's the moment you do light front, you get all the right answers immediately from these simple rules, three-dimensional integrals, no complex integrations. Everything is simple. And you just get these rules. Then you get renormalization. You have to renormalize this, perhaps, in some theories. Well, the renormalization is to subtract delta m from this intermediate line. And that's exactly the same graph, except instead of the denominator from A to C, you do the denominator from B to C. And that automatically, the same numerator with two different denominators, A minus C versus B minus C, gives mass renormalization. It's basically what Bethe discovered when he did the Lamb shift. So you just simply do mass renormalization in a trivial way. And all renormalization is simple in the front form. There's nothing difficult about it. And then you look at graphs like these vacuum graphs, and they never come in because the vacuum has got plus momentum equals 0. Each line's got positive plus momentum. Plus momentum is conserved at every vertex, so you can't go from 0 plus momentum to 3 particles with positive plus momentum. In this case, each of these particles brings in plus momentum, and then you can calculate this graph, no plus momentum. So that's why the vacuum is trivial from the beginning in the front form. In Feynman, you don't think they're trivial, but then you divide them out. You normal order. So you never compute vacuum graphs anyway. So in fact, there is no difference between the Feynman rules and the front form rules because these graphs are already gone. In the Feynman rules, you have to make up a rule to eliminate them. Nothing like that. All right. Okay. So here's then the eigenstate of a light front Hamiltonian. This is the state, these are the wave functions, the 3 quark and so on. These are the Fock states, which are just the creation operators of the free vacuum. Yes?
Can you go back to the slide?
Sure.
So here, assume this, let's say these blue dots are photons.
Yes. 3 photons would be a problem, but here you have 2 electrons in a photon.
I'm not talking about the vacuum, but the exchange.
Oh, here. No problem.
There is also a diagram which is instantaneous.
Oh, yeah. So when you're doing, this is a trivial thing. And I'll explain the rules in a minute. Yes, of course. When you're doing QED, for example, you have not only propagating lines, but the instantaneous lines, and it all works. Okay. So here's again our theory. These are the eigenstates of the light front Hamiltonian, and I want to explain more. The sum of the x is 0 is 1. The sum of k perps is 0. Nothing depends on p plus or p perp. And the p plus conservation is just simply the idea that, in fact, the sum of the x's is 1, and the sum of k perps is 0 is p perp conservation. So I like to reference this paper. It's got 3,000 citations, so people must learn from it already. If you go to the appendix, it has all the light, we call it a light cone by mistake then. It's light front perturbation theory. So if you want to understand all the rules, here's the propagator in light cone gauge, eta dot A equals 0. Eta is in the 4th direction, so you get A plus equals 0. Here's the formula for the polarization. So this gives all the rules for every line. Every line has theta k plus, every line has positive k plus, and so on. And then all the different diagrams, and so on. They each are going out. The perturbation theory rules, and so on. Here's an example of calculations with what you asked, which is the instantaneous lines built in. And then you have to know the spinor algebra. So you do this in Feynman rules, you do this too, but you have to work out the matrix elements of every overlap of spinors. Because in intermediate states, because the particles, the fermions are on the mass shell, you get the fermions in the numerator. So you end up continually doing these things. So you just teach the computer these rules, and of course you calculate anything in any order. So more rules, the definitions of the spinors in front form in terms of their underlying spin, 2 degrees of freedom. And here's the beta salpeter connection too, is that if you integrate over K minus, what Craig talked about, then in fact the beta salpeter amplitude becomes the light front amplitude, because you're eliminating one of the degrees of freedom of the beta salpeter. Beta salpeter has, the K's have 4 vector degrees of freedom. If you integrate over K minus, you're projecting on instantaneous light front time, and then you get the light front wave functions. However, the beta salpeter formalism is harder to use, I think, than light front, because you have to truncate the kernel to get ladder, dress ladder, and so on, and that violates crossing symmetry. In the front form, you never violate any symmetries like that. So, but however, if anybody gives you the beta salpeter wave function as a function of K4 vector, you know how to get the front form guy too. So here's the electron with Jz equals plus a half in terms of its constituents. So the photons here, this is A plus equals 0 gauge, so the photons got physical polarization, plus or minus 1, and these guys add up. Jz always adds up. So you get plus a half here, minus a, and so on. Okay. All right. So then here's what the solutions look like, each of the 4 possibilities, and the wave functions have either m in the numerator or k perp in the numerator, and then they all multiply phi, and phi is just simply the denominator, the initial denominator minus the sum of the particles here, and that's what this is. So it's m squared minus k perp squared plus m squared over x for this guy, minus k perp squared plus lambda squared, if lambda is the photon mass, over 1 minus x. And this is just from the creation annihilation operator. So if you start with this formula, you now know the wave function of the electron in terms of electron and photon. And now you can compute all the observables up to 1 photon approximation. So then all the parameters here are defined and so on. For positronium, we give examples of what positronium looks like in the light front and so on. Okay. And then there's more rules, all right. This is, I think it's the same as the last slide. So here's a recent calculation by Lamb and Lebed, where they actually show the square of the light front wave functions in QED. So this is the electron-positron wave function. And in X, now they put alpha to be 0.3. It's not the real one, you know. So alpha is spread out. I mean, spreads out the thing. So if alpha was 1 over 137, the X becomes very sharp, like right here, because this is mu plus u minus. So then you have the k perp distributions, which are just power law. So it's easy to work out then the light front wave functions for something like positronium. Now, of course, this is just the valence Fock states. Like true muonium is the mu plus mu minus atom. They will be discovering it at JLab soon. There's experiments that are going to find it. And this is the atom of mu plus mu minus. And then you can measure these wave functions. The way you measure them is you take the true muonium beam, which they're going to produce, and you dissociate them in a thin target, and you'll see 2 muons, and one will have x, and the other 1 minus x, so the k perp, the other minus k perp, and what you actually observe is the first derivative of the light front wave function, because you're using Coulomb dissociation of this moving atom. And then you can measure the higher Fock states, because the atoms have mu plus mu minus gamma. They have mu plus mu minus e plus e minus, and so on. So in fact, the wave, when you dissociate the wave function, you can see all the Fock states, and you can actually measure the light front wave functions. So that's interesting. So if you're Mr. Heisenberg, you'll solve this problem by matrix diagonalization. So now I'm going back to 3 plus 1 QCD, non-perturbable QCD, and what is the task? So what you want to do is you write down all the Fock states. They're connected on these off-diagonal matrix elements by a quark, make a quark and a gluon. There's also the instantaneous term that you asked about. And so there's a matrix equation that takes the all the different states, the valence, the higher Fock states, and so on, connects them to themselves through the propagator, and then through, in fact, the interactions. So this is actually a matrix, a Heisenberg matrix problem. You're in Minkowski space. This is not lattice gauge theory. Lattice gauge theory, you don't do things this way. You choose Euclidean space-time. This equation gives you the total answer. There's nothing to do. This is the answer. If you could diagonalize this Hamiltonian, you've solved for the mesons, QQ bar. So this is actually, in principle, the way to solve QCD. You just diagonalize this light front Hamiltonian, and it gives you, in fact, all the masses, and it gives you, for every mass, it gives you the eigenstate, which is the projection on these Fock states. Okay. So here's, in fact, another graphology of it. In fact, you start with the Q bar Q, you get the instantaneous interactions, then you get interactions which you get Q bar Q goes to glue glue. So you get a whole matrix of terms. And this is the way nature solves QCD. This is as close as it is. We're not going to Euclidean space. There's nothing, every degree of freedom is physical. The gluons only have 2 degrees of freedom. There's no ghosts. And you're in Minkowski space, and everything is causal. So when you solve this thing, there's no fermion doubling, by the way. The vacuum's trivial. There's no ghosts. So I always joke, in another planet, this is the way they think about QCD. They just think about solving the problem. So I'll explain more. But this is, in fact, the way to think about QCD as a matrix problem. And you can do positronium explicitly. And that's what Lamb and Lebed did, in fact, in that previous thing. They just solved this, but only keeping the first couple terms of interaction. So this is what you do for QCD. Of course, this becomes a mammoth problem for 3+1 QCD to really do this problem. But let me emphasize something else. In lattice theory, when you look at the states of different n, that's the radial excitations, they have different nodes, right? The radial counter, the wave function vanishes at different nodes as you go up in n. You can only get really one state in lattice gauge theory because you're looking for the energy of the state in a time decay. You write the answer as e to the minus energy over times time, but it's Euclidean space. To get back to Minkowski space is incredible. Now there's tricks for doing it, but basically you only get the lowest state. Here, you get every state. There's no discrimination. Okay? So this is a problem called, putting this on the computer is called discrete light cone quantization. So how do you put it on the computer? You actually use periodic or anti-periodic boundary conditions, and then these variables become discrete, and then you can give it to the computer. So this is light front QCD. It's the Heisenberg equation. Discrete light cone quantization was the name for this. It should have been light front quantization. I regret that. And you can solve the theory. Now what we did is actually, Hornbostel, Pauly, and I did solve this for 1+1 QCD. You can do this procedure for any quantum field theory for 1+1, and Klebanoff has written many papers solving 1+1 quantum field theories exactly this way. But for QCD 1+1, this is a perfect method because you can just diagonalize this Hamiltonian. There's no gluon degrees of freedom because in the light cone gauge, there's no gluons in 1+1. There's only the instantaneous interaction. So it's much simpler. So you can give this to the computer, and out comes the solution. So here's the baryons, the 3-quark baryons. It actually shows, in fact, the 3-quark valence wave function and the 5-quark wave function. You see all sorts of interesting things in the wave function, in fact. And you actually get the states, the meson states, and the baryon states. And you can do this for any number of colors and flavor. If you put the number of colors to infinity, that's the 't Hooft solution, immediately this light front equation becomes the 't Hooft equation, and it's an equation of free vector fields. So but here I'm talking about QCD in 1+1 with 3 colors right here. But you can do any number of colors. So this is actually the way, in fact, you can solve the problem on the computer. And I've asked my lattice gauge theory people, why don't you try lattice gauge theory for 1 plus 1, QCD? See if the method is sound. And they won't do it. They say, we won't waste our time on 1 plus 1. Really? We know the solution for 1 plus 1. It's very intricate and complicated. Why don't they try it? I'm challenging them. So there are any lattice people here? Okay, then you got to try it. Try 1 plus 1 and see if you get the same answer. Because this is the answer. If you increase, so what happens here is you use periodic boundary conditions. So that means, in fact, that P plus is 2 pi over L times an integer k, capital K. Each particle has K plus is 2 pi over L times an integer n. The sum of the n's is equal to K. So actually we use anti-periodic boundary conditions, that's simpler. And then you pick a K like 13, and then the particles have, the sum of their pluses has to add up to 13. The n's have to add up to 13. And then you do it over again, so that's these dots right here, because you just get the points at this K plus over K. That's really K plus over P plus. And then what happens is that if you increase this harmonic resolution, this capital K, from 13 to 115 or something, then you get more and more points. But we found in practice, you always get the same curve. You just...
I think that people do 1 plus 1 lattice calculation.
Really? Has there been?
But it's not Kursanian approach, it's called Saskin approach.
Yeah. Oh, that's right. Yeah. No, so there is a method of that's right. There's also Pearson and so people have tried combining lattice gauge theory with 1 plus 1 DLCQ. And that's another method, and so, but it hasn't been successful. I'm going to explain eventually something called basis light front quantization, which is becoming practical for 3 plus 1 now. So now I'll explain that. Okay. But anyway, you can solve DLCQ, you can solve QCD 1 plus 1. Any quark masses are put in, and any flavors and colors. Okay. So the solutions, though, so let's go back to 3 plus 1, and imagine we could actually solve this problem. We'll get the 3-quark system for the proton, 3 quarks in a gluon, 5 quarks, 7 quarks, and so on. And now these higher ones have the higher Fock states because you have diagrams where gluons produce extra quark anti-quark pairs and so on. But the surprise is that S bar is not S. I don't know if you know this, but normally you're taught that a gluon makes SS bar symmetrically, right? There might be high order corrections. But that's not true if you put in the diagrams where the strange quark is multiply connected to the valence quarks, and then you find the S and S bar are different. And you know that's true because the proton can fluctuate to K lambda, and the S bar and the K-on is not the same distribution as the S and the lambda. So you already know there's a hint from physics that they can't be the same. But also, if you look at the data, U bar is nothing like D bar. They're totally different. And that means that the non-perturbative answer is nothing like de Glapp evolution. Gluon splitting is only a primitive approximation to the right answer. U bar is not D bar. And then also the same diagrams that produce S bar not S, these are diagrams where the gluons multiply connected to the valence quarks. They produce charm quarks and bottom quarks at high X. In my third lecture, I will go through and show the evidence for this. But that's what you get from the theory. That's because the wave functions like to be off-shell minimally in invariant mass. So when you compute the off-shellness, it's the proton mass squared minus the sum minus the invariant mass squared of the constituents, it's off-shell. That's just like Schrödinger wave functions. They're off-shell in energy, but on-shell in the eigenvalue. So when you do that, however, you find the wave functions prefer to be minimally off-shell. That's what happens in bound state problems. But minimally off-shell actually corresponds to the charm and bottom quarks at high X, not at low X. And that's what you find in the solutions. All right. So again, everything at fixed light front time. All right. There's another thing too. When you do the deuteron, it has a 6-quark Fock state, but there's actually 5 different color singlet combinations that make a color singlet deuteron. If you take 6 quarks and assign the color, of course you get the 2 the neutron proton, that's two guys. But you also get higher Fock states, and they're all mixed into the deuteron, and that's called hidden color.
So these constituents, like these clocks, should I think of them as like hard clocks, like a mass of light clocks like vitamin D, or these dressed?
You can think of both ways, but at this point, they're just they're what you create on the Fock state basis. So they're just the undressed quarks. But the wave function does have in it all the physics where the lines are dressed. You know, so in QED, the positronium, you're getting the graphs where the photon is dressing the electron and positron. So I don't know what the right language is. It's really, the Fock basis is the free Fock basis, but the degrees of freedom are in fact the dressed lines. So it has the hyperfine splitting, it has the lamp shift, and all the rest. It's all built in. Hidden color, little statement. As I said, there's 5 different color singlets of 6 color triplets. Just one state is NP. You also get states like delta delta in the deuteron. You can actually measure that. And you can also note that the hidden color degrees of freedom dominate the form factor of the deuteron. So that's also interesting. When you compute the deuteron, people just think it's a loosely bound proton-neutron. You cannot get the observed form factor that way. You have to put in the hidden color degrees of freedom. And then there's also possibilities of other exotic states, which is like this. You could have actually hexaquarks or hexons, which have got 3 diquarks. Perhaps one of them is spin 1, 2 of them is spin 0, and so on. This can be the deuteron, one of the deuteron degrees of freedom. It's spin 1. So this is an example of hidden color degrees of freedom. It's a hexaquark. Now, if you know the light front wave functions, then there's formulas for each of these guys. Every TMD, some of you work on TMDs, some are GPDs and so on, they all have formulas in terms of the light front wave functions. Because the light front wave functions are the eigensolutions of the hadron. And when you're making observations like a transverse momentum distribution, you're starting with the dynamics of the proton, say, and then measuring the quark distributions, and that's the TMD, in both X and K-perp. The X is the light front fraction, and the K-perp is the transverse momentum. So all these things have formulas. I stole this from Lorsay and Pasquini, this graph. But given them, some people say Wigner functions. Actually, it's just the light front wave functions. Okay. So here's a famous formula. This is Drell-Yan-West. So what you do is you pick a frame so that the photon brings in Q plus equals 0. That's an ingenious trick. If you don't do that, it's much more complicated. But this simplifies the analysis. So now what happens, because Q plus is 0, the X here stays the X here. The K-perp changes from K-perp to Q-perp. So the form factor is calculating the overlap between the wave function psi of X and K-perp. I've left off the spin degrees of freedom. And here's the final state, psi of X and K-perp prime. Now first you might think that this K-perp prime is just K-perp plus Q-perp and these guys are unchanged. But that's not true because this guy is going along P plus Q-perp. So when you analyze this component relative to the Q-perp, then it's 1 minus X Q-perp. And then the spectators, the unstruck guys, is K-perp minus X Q-perp. So this is an exact formula. If you sum over all Fock states, nothing is missing. But in practice, you just do the valence or something like that. But it's really an exact formula. The current matrix elements. It's rather beautiful. So this is just showing, in fact, that you take J plus between P and P plus Q and you get the form factor. Again, everything at fixed light front time. Okay. Form factors are overlaps. And you know the wave function here and the P and P plus Q because the wave function is the same wave function. It's psi of X and K-perp, psi of X and K-perp. There's no boosts involved because boosts are trivial in the front form. Because the wave function, the internal wave function, is the same wave function, independent of the total momentum. So that's pretty good. So here's the formula for the For the F2 form factor, it's basically the same thing. However, in this case, for F2, the proton spin starts at -1/2 in this, you could write JZ here. It's the same thing. And it goes from -1/2 to +1/2. So the F2 form factor in the front form is the overlap of the light front wave functions when, in fact, the spin of the initial state is different than the final state. However, the constituents, you come in again with Q plus equals 0 and Q perp, and so you get the same, the spin of these guys is the same as this guy, because spin is conserved by the plus momentum. So this is very simple, and Joe and I gave a paper of this where all the details are there, and it's just, in fact, overlap of light front wave functions, and there's kinematic formulas, the denominator QX plus IQY. So when you do that, you get the right formula for the electron form factors. For example, you put the electron Fock states in, you get the electron form factors. So here's a paper which has got it all in detail, where you use these two-particle wave functions, and then you calculate, for example, the Pauli form factor. It's the overlap of up and down, and you just go through the algebra. You end up with this formula right here. And here's the formula for F2 of Q squared in terms of just this light front wave functions. And you have the usual formula for the anomalous moment. It's F1 of 0 plus F2 of 0 and so on. Here's F2 of Q squared. And when you do F2 of 0, you get this nice formula. Here, actually, the internal mass is the same as the external mass for the electron. So this is just 1 minus x, and so on. And when you just calculate this formula, you immediately get alpha over 2 pi. So this is the Schwinger calculation done with light front perturbation theory. It's very simple. So this formula is your lambda is equal to 0, m squared is equal to m squared. You just get the integral dx times x, basically, and you get times 1 minus x, you get a half. It's alpha over 2 pi. And then you also, here's the formulas then for the light front wave function, and here's the formula for the quark distribution. This is the structure function, just the squares of the light front wave function, and so on. Okay. And here's the formula for the beta-salpeter equation that I described before. You integrate over k minus. It's the beta-salpeter wave function evaluated at fixed light front time. So here, as I described before, you get this beautiful light front wave function and representation of the form factors. And now let me compare that. Mention this point, which is interesting. For the graviton, it's the same formulas, except now you replace the photon by an external graviton. And now it turns out there's 3 form factors called A, B, and C. A of 0 is 1, that's the mass renormalization. But B of Q squared is like the Pauli form factor. And B of 0 is called the anomalous gravitomagnetic moment. And there's a theorem by Turayev and Okun that B of 0 is equal to 0. And that's remarkable, because when you, like in the electron, we got alpha over 2 pi. When you do the electron calculation for the graviton, you get alpha over 3 pi, because there's an x squared in the numerator, not x. That gives you, instead of integral dx times x, you get integral x squared, gives you 1/3. But then there's another diagram where the graviton hits the photon in flight. That gives you minus alpha over 3 pi. And then you get 0. So in fact, it's easy to show in the front form, just by JZ conservation, that you get, in fact, B of 0 for every Fock state. So that's rather remarkable. And this is the only proof, in fact, aside from Turayev and Okun, who proved it formally from general relativity, that you have to get B of 0 equals 0. But it's still true. Okay. Now, as I said before, the Wick theorem, if you try to compute this calculation, this Feynman calculation, in terms of time-ordered perturbation theory, then you get all these graphs. So each of these vertical lines represents a time-ordered intermediate state. So this is old-fashioned perturbation theory. There's 6 diagrams. There's n factorial diagrams. And indeed, if you add them all together, they're each frame dependent, you get the right answer, but each one's non-analytic because it's got square roots in the denominator. It's terrible. But this graph is particularly amazing because this is a graph where electron, positron, photon comes out of the vacuum and the photon hits it. Unless you include that graph, you get the wrong answer. So in instant form, you have to include that. In front form, you only get one graph, this graph. There's no other graph because you've already picked q plus equals 0 here. So this line's are only, you can't have q plus equals 0 go to two positive k pluses. So all these graphs are 0. This graph is also 0 because 3 guys go into the vacuum. You can't have that either. This graph is 0 because 3 guys started from the vacuum. So the only graph is this graph. And that's all you compute in the front form. In the instant form, you have to include all these diagrams. For example, let me just say one thing. For the proton, for example, you have to include quark-antiquark gluon coming out of the vacuum. In instant form, unless you include all diagrams, where out of the vacuum comes quark-antiquark glue and so on, and the photon hits that graph, like that one, you're dead. That's why there is no formula for the front form. Not only do you have the problem of computing graphs like this, but you don't even know how to boost from P to P plus Q. Because, as Dirac emphasized, boosts are dynamical. There's no simple formula for boosts in the instant form. That's why it just totally stopped. Physics stopped when they did this. It wasn't until Feynman invented Feynman rules that we had this idea. But in fact, if Dirac had come in and told people, why don't we use front form? They would have noticed there's only one graph, this one. So just this graph. If you pick q plus equals 0, these are gone, these are gone. And that's the exact answer. Okay. So again, no, I'm sorry, I interrupted you.
So you showed why one of the diagrams that you would kind of naively draw following the old-fashioned notation.
Yeah, instant form, exactly.
Is there a way to see before drawing them that they should vanish? Because otherwise you have to draw them anyway.
Okay, so the main rule in front form is that the plus momentum are all positive, and plus momentum is conserved. So that's all you need to eliminate all those graphs. So that's all it is. So now people derive, I should mention, people derive this by using the infomomentum frame. Weinberg started that. So instead of front form, you can use old-fashioned perturbation theory and take an observer moving at infinite momentum in the negative z direction, and then it turns out you get the same rules. But that's sort of a trick. It's really just to confirm we got the right algebra. But however, it violates all your principles. Nobody moves at infinite momentum, and it violates Lorentz invariance, so why do that, you know? But it's a trick, and tricks are useful sometimes. All right. So here, just to say this, nobody knows how to boost between P to P plus Q in instant form. Front form, it's trivial. There is no boost dependence. You have to couple currents to the vacuum. Even after normal ordering, these graphs are there. Each time ordered graph is frame dependent. You have to divide by disconnected vacuum graphs, instant form. You even have acausal boundary conditions. Very bad. I said all this. I think I'll skip this slide. But I'll just show you something that I got involved with my early years at SLAC, and I'll show you why I discovered the front form. So this is the Drell-Herrn-Gerasimov sum rule. And it's a beautiful sum rule. It tells you the integral of the photoabsorption cross-section for parallel minus anti-parallel is given by the anomalous moment squared. It's an incredible sum rule. It's proof from dispersion theory, unsubtracted dispersion relation, and the fact that the anomalous moment squared is the first term in the low energy theorem after the Thomson term. So when you do the Thomson low energy theorem, you got the famous Thomson term, but then a term proportional to the anomalous moment squared. So when you use this, you find, in fact, this result. However, Barton and Dombey will go down in history because they wrote a paper saying that even if the Drell-Herrn-Gerasimov sum rule is right for the proton and neutron, It's false for the deuteron. And they proved it. And Sid Drell was screaming his head off. He says, how could anybody believe this? The theorem is so simple. It just comes from dispersion theory and the low energy theorem. How could you get a wrong answer? So he asked Joel Premack, who was his student at the time, he's now a astrophysicist, and Joel brought me bit. He says, what did they do wrong? So this is the point. We calculated that the whole thing, and then we looked at the instant form wave function, and what appears in Barton and Dombey is this spinner combination, the product of two spinners, like this. It's actually what you get if you apply two Wigner boosts, or Mellish boosts, you get that. However, that's not the right answer. If you do the calculation correctly, it turns out that it's not just this term here, it's got new terms involving sigma dot capital P and sigma dot little p. It's very complicated. The correct boost in the instant form is not what you think it is. It's not the product of two Mellish transforms. When you put this extra term in, you get the Drell-Hearn-Gerasimov-Sumrall right. Hugh Osborne also did this right too. But what's interesting though to us is that before we had a chance to publish this result, another paper came out from the University of Sussex by Dombian, and it says that not only is the Drell-Hearn-Sumrall wrong, the low energy theorem is wrong. But that was the same mistake. They used this instead of this. So this taught me how complicated boosts are to do in the instant form. Once you do it in the front form, no problem. Easy calculations. Okay. So here's our answer from Premack and myself. This is the boosted deuteron wave function, for example, with all these forms. Okay. So, advantage of the front form. Light front time-ordered perturbation theory. You can do that. You can start with any Feynman diagram and do light front time-ordered perturbation theory. You get just the diagrams which survive. Each diagram is frame independent. There's very few diagrams that have plus momentum positive. JZ is conserved at every vertex. It's automatically normal ordered. There is no, the light front vacuum is trivial up to what's called zero modes. I'll come back to that in another lecture. Renormalization. I wrote a paper with Brodsky and Swaya where we worked out renormalization theory for the electron QED. We did the 1 loop, 2 loop, and part of the 3 loops. We did vacuum polarization, wave function normalization, everything. So that's the whole thing. You can do the Park-Taylor amplitudes and use light front, and much easier than Feynman rules. Park-Taylor is 2 gluon goes to n gluons. Hadronization of the amplitude level with confinement, I'll explain that later. All right. You get this JZ conservation rule, Fock state by Fock state. Every vertex in Fock state satisfies this. And here's the formula for orbital momentum. Somebody asked about this. So LZ here is just like P, X cross P, but in the transverse direction. Here's a nice formula I did with Blankenbecker and Gunyon back in the 70s. If you have the K plus P scattering, they can exchange an up quark. And that amplitude is easily computed in front form. It turns out it's just the product of the light front wave function here, light front wave function here, here and here. There's 4 light front wave functions. And there's one factor called delta, which is just the total energy squared, the invariant mass squared of the interstitial state, minus the sum of the constituent guys. Turns out that this graph simplifies in an amazing way when you calculate in front form. And then you get this simple answer. And then it turns out that the answer just plugging in, you get 1 over, at large momentum, it's 1 over u, 1 over t squared, where t and u are the Mandel-Stanley invariants. And you put that into the formula for cross sections. And by the way, in the non-relativistic limit, this is called spin exchange, electron exchange in atomic physics. And here's the data. It shows us 1 over ut squared is perfect, actually, with the data. So, and also the power law behavior is correct, too. It also, in Reggie language, when you fit an amplitude to s to the alpha at fixed t, Remember, there's a 1 over u, and 1 over u is the same as 1 over s at fixed t, and that becomes minus 1. So this is a region negative integer. And that's what happens at large momentum transfer, that actually regions, which you normally think are positive powers, become negative powers. So that's interesting. Okay. This is the, I think I'll skip this, but there's a whole analysis of cluster decomposition for relativistic systems where this amplitude factorizes in terms of two things, each of which are identical. So you get cluster decomposition agreeing with non-relativistic intuition, even for relativistic theory. Then there's the hadron distribution amplitude. This is defined from the light front wave function by integral over k perp. So this is something that I introduced with Lepage. This is called the distribution amplitude, and Craig talked about it. So this is the wave function of a meson. You start with the valence wave function, you integrate over k perp up to q. So this is actually the basic amplitude for x and 1 minus x. And this is the thing that obeys what's called herbal evolution, Efremov-Radushkin, Brodsky, Lepage evolution. And it's a thing that starts out, like, as Craig said, like the square root of x1 minus x, and evolves to x1 minus x, when you put it all the gluon radial corrections. So that's, I could spend hours on the perturbative Q-city evolution formulas and so on. And here's some of the credit. All right. And then I mentioned before gravitational form factors A, B, and C for T mu nu matrix elements. Here's A of Q squared, A of 0 is 1, and B of 0 is 0. That's the formula. And then I wanted to introduce this. How much time do I have? 4 minutes, okay. So this is called the Sivers effect in the literature. I wrote a paper with Daiseng Wang and Ivan Schmidt, and we calculated this amplitude. So this is electron scattering on a proton with a polarized proton out of the plane of the screen. And people measure, following Sivers' suggestion, the correlation between the proton spin, SP, and the direction of the photon and the direction of the jet. And that's called the Sivers effect. However, if you look at it, it looks like it's T odd, because this changes under time reversal, and this changes, and this changes. So Collins published a paper saying it's 0. However, we didn't know this. We didn't know Sivers even had suggested this amplitude. We just computed it. And we put in the gluon final state interactions here. This is final state interactions, deep elastic scattering. This is not in the Parton model. Parton model, you pretend as if final state interactions are irrelevant. They're not irrelevant. And in fact, they're leading twists. They never go away with Q squared. So you put in all the gluon interactions, and this now becomes, in fact, the amplitude has an I, because it's an intermediate state here. So in fact, this amplitude is very interesting, because it's the first example that the usual analysis of the Parton model is wrong. That initial state interactions and final state interactions actually contribute, and they're not power law suppressed. So this is measured at COMPASS and other experiments, and they find it's non-zero. And Danny Sivers, to his credit, is the first one to emphasize this is observable, and we're the first ones to compute this. So I sent the paper to Howard Georgi at Physics Letters B, and a week later he sends it back. And he says, Stan, he says, not only have I accepted your paper for PLB, I have checked the calculation myself. I was astounded. Why did he check it? Well, he recognized, number one, that Collins had shown it was 0. And he recognized that it's leading twist. It's not power law suppressed. But if I didn't know front form, I could never have done this calculation, And then Collins, to his credit, John Collins, a month later, he wrote another paper saying that not only was his own paper wrong, it doesn't violate time reversal, He agrees with Brodsky and Wang and Schmidt, and then he extended this to the Drell-Yan process for initial state interaction, where the sign reverses. Actually, we had done this too. We published at the same time. But this is really important. It shows, in fact, that all processes in hadron physics are influenced by initial state and final state interactions. So this is really beautiful. It involves the light front wave function here. You have to put in both the S wave and P wave. So let me explain that real quickly. They'll come back later. That the proton always, if you think about its quark diquark, as was introduced by Craig, then there's both the S wave and P wave between the quark and the diquark. Unless you have both, you don't get an anomalous moment. The magnetic moment of the proton depends on having both the S wave and the P wave. When you put that in, the S wave gets a final state interaction. It gets what's called a Coulomb phase in QED. But the P wave also gets a Coulomb phase, and they're different, and the interference is what gives you this observable. So that's how subtle this is. So it's a pseudo-Tiad observable. It's leading twist. It violates perturbative QC factorization, and the sign reverses in Drell-Yan. Okay. So I'll just say this last slide, I'm sorry. That when you compute structure functions, it's just the square of the light front wave function. Same for the TMD. In the case of structure functions, you integrate over all x's except the quark that you strike, and you integrate over all k perps. In the case of the TMD, you integrate over all the quark x's and k, but not the one k x and k perp of the struck guy. So it's a square. I call this the static approximation, just the square of the wave function. You get the square of the wave function. There's no Wilson line effect. It's probability. It's process independent. You get all the right observables. It doesn't give what's called shadowing and anti-shadowing. I'm going to come back to that. It's too simple. But it has all the sum rules, momentum sum rules, and so on, JZ sum rules. It has de-Glap evolution, but does not have things like diffractive deep elastic scattering. However, when you do dynamic calculation, then you have, in fact, the final state interactions, and then you get all sorts of new phenomena. You get the modification of rescattering. You get the Wilson line effect. You lose probabilistic interpretation of this, because some things are modified. Process dependent, because the collision itself with the spectators changes the answer. It's T-odd, like the Sivers effect, pseudo-T-odd. It gives you phenomena like shadowing and anti-shadowing. I'll come back to that. Some rules are not proven. In fact, I think they're wrong. You still have evolution, and you have diffractive deep elastic scattering as well. So I'm going to stop here. Okay. It's hard to hear through this.